envisaged by Dr. Avinash Chander while taking over as the DG DRDO on May 31st last year. Apart from expressing his commitment towards performance and timely delivery of critical programs like LCA, artillery guns, and surface to air missiles, he had expressed his desire to make DRDO a leading technology agency in the world. For this to happen, he had emphasized the need to involve academia in a very close interaction. True to his commitment, Dr. Chander is today with us, and he is there to evoke that very close interaction with his detailed roadmap, what we has envisaged for interfacing DRDO with the academia. I welcome sir for his keynote address.
Dr. Dubey, Dr. Chaube, Dr. Satish Kumar, Raghav Mittal, members from the academia, members from the armed forces, DRDO, media, and most important, the team engineering watch which has made it happen. I must thank this DRDO engineering watch effort to bring this event at a time when we are really looking to move several steps up the technology ladder. Satish has covered a lot of areas where we have in the past interacted with the academia, which has brought a major change. But technology is not a static thing. It's a constantly changing and changing at a much faster pace than ever. And I don't think any government-owned organization can really be the sole authority of the technology mandate or the technology change. I think it has to emerge from the entire scientific community in the country, and that's where we are looking how to build that vast resource potential into an effective research arm of the nation. And that's where, for the defense particularly, we need both pure research, which will define new futures, but more important, a directed basic research, which would create new capabilities and new technologies for us. Now let's see. Our vision for the emerging India is a fully developed and secure nation and have a high human development index. Naturally, this will require education, health, agriculture, industrial development, economy, creating wealth, and technology and wealth are strongly correlated. We have seen world over, technology leader becomes also the economic leader. And to make it happen, a very strong, secure India and the secure defense, strong defense forces. At the same time, our vulnerabilities are also expanding. We all know what's the ambience around India. In fact, India has got one of the worst climates, security climates in the world today, perhaps leaving Israel, or maybe worse than Israel in some ways, because our adversaries are much more potent. And then we have the asymmetric engagements, pandemic changing climate conditions. We are seeing the monsoon shortage today, water sharing, or rivers coming from abroad across the borders, energy security, or sea lanes. We have seen what happened in Iraq and how it will affect our oil availability. So all this requires new solutions all the time. New technology, new capabilities, new ways, innovative ways of finding this solution. And that can happen only through the technology education, collaborative research, and the entire team working together. If we see in terms of the defense requirements, military preparedness primarily evolves from the environment, which is our threat perceptions. What are our threats? What are our responses we want? What kind of preparedness we need to have? How much is our concern with respect to west? How much is the concern with respect to north? And that will define our security priorities, because we have limited resources, how to allocate those resources, convert into doctrines, what should be our philosophy, whether no first attack, defense oriented, limited thrust inside, and all that will decide what type of products you need to have, what type of technologies you need to create, what type of capability we need to build. And then we'll start the other left half of the chain to keep those technologies. Where do you innovate? How do you convert that innovation into a capability? And then how do you convert that capability into a defense technology, defense product, where you require the processing, manufacturing technologies? So right from the fundamental knowledge of science, from the knowledge of principles to the technology, process, and the manufacturing converting into product, the entire chain has to be covered as a part of the scientific effort. And that is where the technology development challenge lies. First, to create a new knowledge, convert that knowledge into a technology, and then convert the technology into an engineering product. And having that product, find different functionalities for the same product. Because today if I make a tank, I find that the same tank can be converted into 7 other accessorial products, which can be the minesweeper, which can be the man carrier, which can be... So it's not just a tank I'm making a whole array of capabilities. And then the need for new tools and new knowledge. And the most difficult part is, if we say about 55 years back when DRDO started, we could afford 15 years, 20 years for a development cycle. The technologies were stable. If you see, the arms once imported will go on for 50 years. But today, the life of a technology is coming down to 15 to 20 years. Correspondingly, the development cycles also have to change to 5 to 10 years. And that is where the enhanced velocity of R&D, rapid fielding, converting into a usable product, the entire cycle of what I have said, the knowledge to technology to product, has to be condensed into a much shorter time frame, and that requires involvement and innovation at all levels of scientific effort. And if you just see the exercise which goes into a technology evolution. For example, if I want, when we started the NOG missile, we did not have an IIR seeker, infrared imaging seeker, but we wanted to take on. So we started with the concept of the missile, starting with a daylight seeker in that, normal simple camera, worked on an RF seeker parallelly, worked out what type of devices to develop on that, converted it to a proof of concept, prototype, product, and in the process, there were a lot of expected results did not come, entire cycle had to be changed, the device what we thought will come did not materialize. And as you see, all these loops what are shown here how they got really went through in a single product like NAG. And this is in each new product what we design, this cycle of hypothesis to proof of concept, prototype, product, then test and evaluation, users feedback comes, and then in this process of product generation, the technology keeps evolving. For example, LCA, when we started, and 93 when we started the first prototype development, from that to what technologies has today and what we are planning for tomorrow, is a vast change, because it has to remain contemporary. So in the process of technology evolution, there has to be a constant process of upgradation built into it. So new ideas, new processes have to be an integral part of any development. And in this entire process of science, knowledge, evolution to technology and product, DRDO has to provide technology solutions to the armed forces, develop new capabilities, cutting edge technologies, explore new knowledge in the frontiers of science, and because without that you cannot have cutting edge capabilities, and create a technology superiority on both sides, from the science side, the concept, and on the other side, the engineering to the product. So DRDO is the kind of interface between the knowledge generation to the product at the industry, and that's the main role of converting knowledge to a defense product. And what are the new initiatives what we are going? We are doing a lot of things. So far DRDO has been primarily into what I call a technology chasing mode. Whatever we are buying, how to make a somewhat better product, how to make a product which is available elsewhere. But I think today we have crossed a threshold of development where we need not just do what has been done. We need to look at what needs to be done and how it can be done. And that's where we look at next generation aerodynamics and propulsion, hypersonic vehicles where nobody in the world has succeeded so far. The best has been done by US, 316 seconds of flight so far, yet to convert into a product. Space security is a challenge. You cannot hit an enemy satellite like China did about 5 years back, because the kind of debris creation is simply not acceptable. You have to find innovative solutions how to disable a satellite without hitting it, how to protect your satellites, how to find ways of replenishing, how to modify your capabilities in space. Unmanned autonomous systems are going to be changing the way the wars are fought. And I think this is one area where the armed forces also have to generate new doctrines to create an integration of the unmanned systems into their war fighting strategy. New gen sensors is a continuous process. Directed energy weapons. The future wars are going to be remote non-contact, and directed energy weapons are going to play a major role. Underwater and deep sea operations, access to resources on the land is slowly becoming less and less. We are exhausting the resources very fast. Next part will be to go to underwater. 3/4 of the earth is still underwater. Reach those areas and exploit. Advanced materials. We are looking at rheological materials. We are looking at materials which will densify under stress so that it can protect against a bullet hit much better than any of the existing materials. Futuristic materials which will bend the light. They are actually materials can change the entire process of thinking, entire process of science. Things which were considered impossible earlier, today we are looking at designer materials and they are possible. Cyber systems and securities remains a well-known threat for which we have to keep on finding solutions. Advanced computing and computational techniques. I think we need to start working on path-breaking computation techniques. Quantum computation is already a lot of work going on abroad, but not much in India. Quantum computation linked with the brain processing, the signal processing methodologies in the human mind, I think these two have to be put together to create a new way of computation, and of course the nuclear environment security is one area. What happened? These are to clear it up. And the upcoming challenges are the which we have taken as a products, immediate products for one is the hypersonic technology demonstrator vehicle. As Satish mentioned, scramjet propulsion. Today we are looking at a cruise for a few seconds, Mach 6, but we are now looking at making a system. Stage 1, 600 seconds flight capable of going up to 1500 kilometers. Second stage, 1 hour flight capable of going up to 10,000 kilometers. And that is a type of challenge where you require new materials, new capabilities, understanding of the propulsion, the materials, fuel, and the system technology. This is one major challenge. MIRVs, of course, have been proven elsewhere. This is one of the needs what we are working. Unmanned combat air vehicle. Lot of effort is going on across the world, converting the current manned systems onto unmanned. F-15, how we can use. But in future, we have to design an unmanned combat air vehicle which is designed for autonomy. That's going to be a major challenge. And as I said, directed energy weapons, space-based sensors, and the security. Now let us take a case of underwater and deep sea technology. What do we need? What type of technology challenges it has? We are looking at operational depths beyond 1000 meters. It will require wideband, multiband operations, conformal arrays. All of you know electromagnetic signals will not work, they don't penetrate underwater. So we have to have acoustic conformal arrays, networked sensors, synthetic aperture sonar. We are now looking at a process where you can have a very fine resolution with a synthetic aperture sonar, wire-free sonar suit, stealth in sonar, how to minimize your signatures and how to make sensors which can be at least 20 to 30 dB better sensitivity. It will require new materials. Today we are looking at rubber with proper cavities inside for sensing, but we need new materials which have a much higher sensitivities, a different class of weapons which will work underwater, stealth torpedo, remote operated vehicles, and then a total new concept of deep sea security search, and which will be primarily unmanned. Because you can't have people staying underwater for long durations, so you'll have more and more of remote operations. And this is a major challenge when you're working at 100 bar atmospheric pressure of that kind. How we are going to have, what type of capabilities are needed. There's one thrust area where we are looking with the academic institutions to create a new level of capability. Directed energy weapon. Today, if you want to hit a UAV, you have to be cost effective. I can't launch a 4 crore missile against a 1 crore UAV. It is an economic ruin. So we need to find low cost, repeatable weapons, and that's where directed energy weapons become the challenge. And when we are talking of creating megawatts of energy focused to sub-micro radian, so that at a distance of tens of kilometers, and subsequently if you are looking at space, hundreds of kilometers, you are looking at a patch size not more than a few centimeters. It becomes a totally different level of manufacturing processes, the type of control processes, the mirror accuracy is what you need, the understanding of the optics in the atmosphere, the dispersion and diffraction, high energy effects in ionizing the atmosphere. Each one of them we have to understand, we have to build the new capabilities, and then how to harness micropower for wave power for these applications. And these become the new challenges. Once again, one lab of 40 people, 50 people cannot do this job. This has to be done by a group of academicians, institutes across the country. Each one has to take on challenges and come up with solutions. If we want to become a world leader in technology, it's not the job of government, it's not the job of DRDO, it's not the job of any scientific, it's the job of each of us as an individual that we have to lead to that goal. Unmanned battlefield, if you look at that, this poses another set of challenges. When I'm talking of, we are now working on a soldier assist robo. If I want a 100 kg, 120 kg, and I want a protection against simple things like a bulletproof protection, it's good to see on a movie screen a huge mass of steel. But when you are looking at a 120 kg robo, and today's technology says that 20 kg per meter square is the weight of the protection material for small arm. The weight of protection itself becomes 100 kg. So we need to have better materials. We need to have different way of looking. That's why I said we need materials which will densify against impact and provide a resistance to the bullet instead of allowing a sheer damage to lose the energy. So we have to find innovative ways of solving these problems, and that will require challenges in the power, challenges in the strength of materials, challenges in the way they communicate, bandwidth management, cognitive technologies, assessment of threat, signal management, relative movements, kinematics, and that's where the unmanned battlefield. We are starting a new institute concentrating on the robotics, where we want people to come from different institutes, contribute, work. I'll come into more of that later. Materials is the heart of any scientific effort, and unfortunately today materials is one of the weakest parts in our Indian technology capabilities. If we see, if we want a lightweight aircraft, I need aluminum lithium alloys. We don't have. If I need to make a IC device, I don't have the silicon of the requisite purity wafers. If I want to have a high power transmitter, I need gallium nitride and beyond, which we don't have. So similarly, when I look at the materials, polymer materials, I look at high temperature materials for our hypersonic engines. Finally, I find that in each area the limiting factor becomes the material. And that's where I think we have Dr. Sundarajan, we have many more material specialists. I think the nation needs to create. We have already started a materials initiative. Dr. Banerjee's of ISC is getting together a group working out a material strategy, what all, where and how we can do. But this is again a challenge where we have to put an effort, because this doesn't require too much of investment or anything. It requires effort, it requires thought, it requires ideas. And if we see, these are some of the examples, we have many similar needs. And when we see the criteria for our technology strategy, as I said, DRDO is the interface between the academia and the industry practically, because DRDO is a technology developer which converts knowledge to technology. So today, R&D industry users are getting into the make category items. In fact, industry R&D is practically non-existent, unfortunately, in the country. And that's one of the major drawbacks. If you see world over, whether it's China, whether it's US, a bulk of the R&D is done in the industry. And only a small part is done in the government sector. Whereas in India it is not only reverse, it is a much higher percentage also. So first is that industry has to develop in R&D. Universities have to take on projects. In fact, our aim is today, DRDO is spending about 20 to 25 crores per year in academia interactive projects. Some of them are blue sky research, some of them are directed research. Our aim is that within the next 5 years, we want to enhance this 25 crores to 500 crores. Purely for the academia interaction, directed basic research projects in some of the areas which I have highlighted and some of the areas which I have not described also. Aim is that my time cycle, which today, as you see, is 0 to 30 years, for a product has to be brought down to 0 to 10 years. And we are looking at universities as the right place, and our model of working with universities is that a few scientists from DRDO, 10 to 15 scientists, 40 to 50 professors working, and 500 students, MTech, PhD. That's my forced multiplication. And I want to create many such institutes, and I want these institutes to build to be centers of global level of prominence of capability. I want India to have its own institutes of the caliber of Draper's Institute, Lincoln Institute, JP Labs, and so on. Today we don't have. We have excellent academic institutions, but we don't have research institutions of that caliber. Maybe one or two, TIFR and some, but not many. If we want to be a nation of a developing nation providing technology leadership, I think we have to think big, we have to think in raising ourselves, and this research will drive in turn the economy, it will drive the industry, it will drive a total transformation of the nation. I think the research from here will create opportunities for this research scientist to move on to the industry. That's what we are looking at. It's not just a technology driver, it is a driver for the national opportunity. And how we look at it is that technology is where the readiness levels are 0 to 3, thought to concept. We work with the academic institutions, 0 to 3, 0 to 4, principal investigators. Today we are working with basic scientific investigations, create new knowledge, prove something on the bench, demonstrate the concept. Then DRDO and such like labs come together, convert that knowledge, have a peer knowledge transfer, what I call the transplantation of that knowledge into the DRDO labs. And there it's further nurtured, a plant to become a tree, and then that tree goes to the industry and starts bearing fruits. That's what the model we are looking at. 0 to 3 in the academic institutions, 4 to 6 in the DRDO labs, and then 7 to 9 coming from the industry. As you see, each level will require different kinds of scientific knowledge, different kind of scientific capability, but at the same time, a very strong overlap, strong fusion, strong movement across the layers. People will move with their knowledge, with their product in different domains and keep on changing back. That is how the scientific milieu in the country is going to change, revolutionize, will come out of our mindset that I am only teaching. And we have to think that we are not just teaching, we are creating knowledge capital. We are not just creating human capital, we are creating knowledge capital. And this is where we look at the directed research, start with a perspective plan, system analysis, critical technology and maturity estimations, research roadmap, research alignment. We have got boards, research boards, we have got, I will come further to that. And this is a very continuously revolving cycle. As I said, when I look at the institutes, what we want to create, there is no permanent manpower. Because every 5 years people will change, new ideas will come, there is a continuous flux. It's not becoming a static, stagnant organization. There will always be challenge, there will always be new ideas coming, and that's what we are looking at. A dynamic system, new thought processes flowing. Blue sky research, DRDO has been encouraging for a long time. Aim is to strengthen the national research base, to create facilities in the academic institutions so that they can carry on research, breakthrough innovation, outcome to defense societies, technology leadership, intellectual property creation. And this blue sky research, success rate may be low, but whatever success comes out will be the backbone of the directed research. And our concept is that directed research and the blue sky research in our efforts will be a 70-30 type of activity. So if I am spending 100 crores, 30 crores will go on blue sky research, because generally blue sky research is not a high cost is not involved, but it requires more effort. It requires also a preparedness to take risk and be prepared to not to succeed also. That is where things have to go. This is the model. We have 4 research boards: aeronautics, armaments, naval research board, life sciences board. And now we are proposing 2 more on the electronics and the material sciences, which will encourage thrust in these areas. We are we have committees of academic experts. Each of these boards in turn has various panels to look into the specific areas, and they meet once in about 3 months, take projects, put together, and now we have consolidated this under one umbrella, which Dr. Satish Kumar is now heading. Aim is to consolidate and that all these activities are not allowed to just simply fritter away below threshold efforts, which are we sow the seed but nobody waters it. So we are looking at a new concept where while we are encouraging R&D, it's not just for funding purpose. It is R&D effort to where somebody knows that his knowledge is being sought by and needed somewhere. So that is the aim of this activity, and this is how we are going ahead. We have taken a number of national programs also on the MEMS, on the nano sciences, on the life sciences. And if you see, we have already running established centers at Hyderabad University for high energy materials, where we are looking at today identify the molecule which has a potential for high energy release based on mathematical modeling techniques. It's no longer an experimentation alone. Science of materials has become a mathematical science, where modeling has become a very major tool in that process. We are looking at that. In Bharatiyar's University, we have set up a life sciences research at Coimbatore. We have a first research park of its kind in the country at IIT Madras, Chennai. China has more than 100 such research parks. India has only one. I think this is another area where academic interactions with the research institutions and the industry have to come together through these research parks. Currently, we are quite in an advanced stage of setting up a J.C. Bose Center for Advanced Technology for autonomous soldier, robotic soldier, and the aim of this, as I said, is primarily involving students in the research. And also, these centers are not going to be the centric to that institute. Although it is located in Jadavpur, aim is to harness the capabilities of various institutes in and around that area. Aim is to attract people, anybody can come and work there. Aim is to attract people from abroad, should come to a stature where people want to come and work there. That's the aim we want to create in these institutes. And already we have tied up at least, I think, about 10 to 12 institutes in the eastern region who will be collaborating and working together in J.C. Bose Center. Same way we are now working with IIT Bombay, IIT Madras, Access for a Center for Propulsion Technology, and we are looking at more for the aero materials and so on. And we feel that these centers have the potential to change the way we think and the way we work. The exclusive domains of the academia and the science, research and the industry will get totally merged into one single coherent activity. As I said, we need to set up more centers, and we want to have ideas from the academic institution. Aim is not, I have a lot of inputs, everybody says you set up a center at my place. Aim is not that. Aim is, what are the ideas, what type of technology capability we have, how I am going to enhance the capability by using multiple institutions, set my goals. Each institute must have a set goal, 15 years, 10 years, 15 years, but a general goal, not that I have to meet. And in the process of reaching that goal, you will find many products coming out which can keep on flowing at various levels. Simple case, if I am making a robotic soldier and I need an energy packing density of value X, and today we are having a 0.2X, any enhancement as we move to that goal will be an industry, economy changer. So like that, there will be a lot of outputs coming which will flow into the economy from these efforts as they move up that channel. We are looking at involving scientists from various institutions to get together, DRDO chairs at academic institutions, active collaboration and research linkages with foreign universities where we can work together, and scientist academia exchange program. I think this is one area where we want to send our young scientists, work there for 3 to 5 years, no permanent staff from scientists also. Work there 3 to 5 years, come back, seed those technologies in the labs, move further, so that there is a continuous movement upward on both sides. And finally, our vision is to be a nation with a world-class academic research base, frontiers of science and technology. And I think this vision can be realized with the participation of all of you who are here and all those who are not here also, coming together and making it a reality. Thank you.